Now we will talk about collisions. So mainly in collision, we will see the different types of collision. Elastic collision, again that is your inelastic collision mainly. So that elastic collision, so in the elastic collision, we can say there are two things mainly occurs. So the momentum is going to conserve. So in case of that, so let's say if I just have these two spheres of mass m1 and m2, so then again I can say that so they are moving with a different velocities over here. So let's say both of them, you can say that they're moving with the certain velocity. Let's say this is a u1, again you can say this is your u2. Then again after some time there is a collision between them, and again after collision they also gets separated. So after collision, let's say this is a v2 having the mass m2, m1, again you can say that, so let's say this is v1. So they will just exert the force on each other over here. So this is a sphere A and B for this particular case over here. So now what will happen, the total linear momentum is going to be conserved, means the momentum before collision is same as that of your momentum after collision. So momentum before collision, so that is a m1 u1 plus m2 u2 is equals to, you can say that m1 v1 plus m2 v2. So this is what we called as a total linear momentum is always going to be conserved. Again you can say the total kinetic energy of the system is also conserved, means the kinetic energy before collision is same as that of your kinetic energy after collision. So that is what we can say, for that your energy is also going to be conserved. So after the collision, the body completely regain from their deformities. So that is what we call as a elastic collision over here. So this is about the few properties of your elastic collision over here. The momentum and kinetic energy, both of them are going to conserve over here. Now the next, if I talk about inelastic collision, the total linear momentum is conserved, but the energy is not going to be conserved entirely. Some part of the energy is lost. It might be in the form of, let's say, light, heat, sound, like that. So that is what we can say, the inelastic collision. So after the collision, the bodies stick together and move with common velocity. So that is what we call as a inelastic collision over here. So this is what we have seen in inelastic collision, where after the collision both the bodies stick together and they move as a single unit. So even I can just write it down, m1 u1 plus m2 u2 is equals to, let's say, some common velocity, that is a m1 plus m2 into v. So there is obviously some loss of your kinetic energy, that what we had discussed in inelastic collision over here. So this is how, so the total momentum is conserved, the kinetic energy of the system is not conserved, there is some loss, the body partially regain from their deformities, and some of that kinetic energy is also lost. So again, elastic collision in one dimension. So that is what we had to see. So the same thing that we had discussed, m1 and m2, they are just going to collide with each other over here. So this is moving with the velocity u1, this is nothing but u2. So definitely you can say that your u1 has to be greater than u2 for the collision. Then both of them will just get collides over here. So they will exert the force on each other, equal and opposite. And again after that, they move apart separately. So this is how we can show over here. So this is v2 and this is, you can say that, let's say v1. So you can say that obviously the same principle you can use over here to just write it down, that m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. So that is along the one dimensional. So this is called as a one dimensional your elastic collision over here. So again in two dimensional also you can show over here. So this is a sphere of mass m1 moving with the velocity of u1. So it gets collided over here, then again it will get separated. Yeah, so it makes some angle over here. So this is nothing but after collision you can say that m1 v1 cos theta, m2 v2 cos theta. So for this case the momentum is conserved along the x-axis. So the momentum, you can say that you're along x-axis, you can also write it down over here. So this is what we know, that m1 u1 plus m2 u2. Again we can say that your m1 v1 plus m2 v2. So if I assume that initially m2 is at rest, so this one you can say that along the x-axis your m1 u1. So then again the next thing you can say that after collision, so after collision the direction has been shown over here. So this one you can say that then definitely this is m1 v1 cos theta 1, and similarly you can write it down. So that is a m2 v2 your cos theta. So that is what we can say for this particular case over here. So that is your one of the equation that you can write it down along the x-axis, and similarly the momentum along the y-axis also you can just write it down over here. So even for the y-axis also you can write it down the similar things. So let's say now if it is along y-axis, if it is along y-axis the initial momentum is 0, again the final momentum we can say that, so that is m1 v1 sine theta. Again you can say that, yeah, so m1 v1 you can say that, so this is a sine theta 1. Again you can say for this particular case also, so this is your m2 v2, so that is your sine theta 2. So this is how we can write it down, the formula for your momentum along that y-axis also over here. So initially there is no momentum along y-axis, so since m1 is moving only along your x-axis, again m2 is at rest, so initial momentum is 0. Now after collision, so m1 m2 both moves at some angle theta 1 and theta 2. So since we have to take the momentum along y-axis, you can say that it's m1 v1 sine theta 1 and then m2 v2 sine theta 2. Again according to sign convention you can put the values, but these are the two equations from which you will get the answer over here. So this is what we have seen in the collision over here.